Okay guys, so we're going to do plug flow reactor. So basically we have to understand what is plug flow and why are they calling it plug flow, and it'll make the whole analysis a lot easier. So the first thing is we're dealing with a tubular reactor. So we're going to discuss what plug flow means. Or a plug flow reactor, it's a mathematical model. So what you're doing is, if you see this shaded region, I'm kind of shading it a little darker. Imagine it looks like a plug, right? And it's a differentially small plug. We measure that with dV. So what comes in is FAO, which is your molar flow rate in, and what comes out is your molar flow rate out over that differentially small volume. So there's two things we gotta discuss real quick before we get into how to do the material balance of this plug flow. The first thing is conversion, and that's the symbol up here. I tried to shoot the video before, so I'll rediscuss what that is. So basically, X is conversion. So you can look at it as moles reacted of A over the moles fed of A. Okay? So moles reacted of A, it's another way of saying how much of A disappeared and hence got converted. So the way you can look at it is say, okay, well, let me draw that plug again with the dV. If I had, let's say, 10 moles come in, sorry, I won't call this dV. Let's say we did the analysis, we went a little farther than just the dV. We went a certain volume, V, right? And what's coming out of that plug, or that elongated plug, would be 6 moles. So what was the conversion, right? So you'd say, okay, well, 4 moles reacted. We went from 10 moles of A to 6 moles of A. So you have 4 moles of A that reacted. So then over here, you got 10 moles fed. So let's look at that in the form of a decimal and a percent. So you have 0.4, and it's easier as a percent to understand, but 40% of A is now gone, or hence converted into products. So if your reaction was, I don't know, A goes to B, 40% of A is now gone, and that 40% was converted into B. If it was B plus C, let's say, then 40% of A is gone, and that 40% of A was used to make B and C. Okay, so that's conversion. So the next thing you got to do is we have to know what the incremental step theorem is. It's very simple, sounds complex, but I'm pretty sure once I start it, it'll be a lot easier than it sounds. Okay. So let's say you have the plug. So this is what we're doing. Now this one will be over dV. Before with the conversion we were talking about some distance down the reactor. But now with the incremental step theorem, this is going to come in handy when we do the material balance. Okay. So what is incremental step theorem? Well, let's say you have FAO, and then over that differential volume, you come out with FA. So what is FA equal to? How do you write an expression for FA in terms of FAO? So you could do it like this. FA is equal to FAO, what you start with, plus the characteristic change in the molar flow rate over the change in volume times the change in volume. Now that looks kind of like, okay, what the heck? But the way to look at that is like this. Y is equal to mx plus b. And I'm going to label it on the left, y equals mx plus b, and it becomes a little more straightforward. You got y is your FA, that's your b, your y-intercept, that's your slope, and this is your x. And I kind of think of x as your distance down the reactor, but you're taking an incremental volume down the reactor. So that'd be your x. So if you looked at it, yep, there you go. It's y equals b plus mx, same thing as y equals mx plus b. So we're going to use these two concepts when we do the material balance for the plug flow, and we'll do the calculus in the next video. Okay, I hope that helped.